So now that we have this idea of torque, we can bring in to our definition of equilibrium, we can say our second equilibrium condition is not only do you have to have the forces balanced, but you need to have the torques balanced. Right, so here we have a picture of this concept in action. We have these two children who look like they were in an airline safety manual previously, but now they're playing on a seesaw or a teeter-totter or whatever you want to call it. I think a lot of these have been removed from parks because they're basically death traps. Um, but they're still good for physics, right? So we have a pivot in the middle, right, and that's where the object's going to rotate around if it's going to rotate at all. And there's going to be some force from that pivot, right? But if we look at the calculation that's below the picture, we can say the torque from the pivot, well, that's whatever that force is, times the distance from the pivot point. But the distance from the pivot point is 0. So any force that goes through the pivot point is not going to be able to rotate the object. Right, so that force is important to balance out the downward forces of gravity from the children, right, for the first equilibrium condition, but it's not going to play into calculating the torque. Now, if we look at the torque from the child in the blue overalls, there is, the force points down, and the moment arm is horizontal, right? And it's that distance from where the child is sitting to the pivot point. So we can multiply those two together, and you can see that I haven't included an angle. Well, that's because they are perpendicular to each other, right? So I'm looking for the perpendicular component of the force of gravity in this case. But that would be the entire force in this case, because the force is perpendicular to the moment arm. The other way that you can think of that is just say, well, the sine of 90 degrees, if you wrote down the whole calculation, the sine of 90 degrees is equal to 1. So we can see that if it was just that child on the teeter-totter or the seesaw, it would start to rotate in the counterclockwise direction, so that torque is going to be positive. And the torque that is caused by the child in the pink dress is going to be negative, right? So we need that total torque to be 0 to make the to meet the second equilibrium condition. So because one's positive and one's negative, we know that in principle that's possible, but they have different masses, and so there's going to be different forces. So if we have that situation, right? So let's say that the child on the right is more massive. What can we say about where they need to be positioned in order to make the torques balance out? Right. So what can we say about the moment arms? So should the bigger child sit farther from the pivot than the small child? Should the bigger child sit closer to the pivot? Do they need to be equidistant from the pivot, or does their positioning not matter? So hopefully you saw that the bigger child should sit closer to the pivot point, right? So we have a bigger force, and so therefore if you multiply it by a smaller moment arm, then we can balance out the two torques. So as an example calculation, let's say child 1 has a mass of 20 kilograms and is sitting 2 meters from the pivot point. If child 2 has a mass of 30 kilograms, how far should they sit from the pivot point? So we know that the two torques need to add up to 0. And we already know that torque 1 is going to be given a positive value and torque 2 is going to be given a negative value to stay consistent with our definitions. So they can add up to 0. So we take the force in each case, which is just going to be the mass of the object times g, force of gravity, times the lever arm, and the appropriate sign. Right, we don't have to worry about any angles here because the forces are perpendicular to the moment arms. So we get this expression here. So we can see that g is going to cancel out, and with a little algebraic rearrangement, we can solve that for R2. So we can see that the units work out, and we will get a distance of 1.3 meters. So if the child sat farther away, it would start rotating. So if the heavier child sat farther away, it would start rotating in the clockwise direction. Okay, so I've got this big metal stick or pole that I found in my garage. It's kind of heavy. If I put my hand right at the center of mass, then I can exert with one hand the force that's going to balance the force of gravity. And because the force of gravity acts on the center of mass and my hand is acting in the center of mass, there's no torque on the stick. Now, if I want to, I'm getting a little tired here, so if I get my other hand involved and I balance, spread them out evenly around the center of mass, then I can hold it with my palms up and, I've got about half the weight in each of my hands. And because my hands are, this hand on its own, the right hand, would exert a torque that way, and the left hand would exert a torque the other way, but because they're equidistant from the center of mass, their torques are also going to balance out. Now, maybe you've had this experience trying to carry a heavy piece of furniture with someone, right? If you end up being real close to the center of mass and the other person's far away, right now I can feel that my left hand is supporting a lot more weight than my right hand. And that's because they're still adding up to the total weight of the stick, but because of the torque, to balance out, this hand has to exert a lot less force, right? So you wouldn't want to carry something like this with a friend. Now, things get really difficult if I move it so that the center of mass is not in between my hands anymore, right? And I can't even really do it with my palms up. It's pretty heavy. But if I turn this hand over, if I need to hold it near the end, now it's a lot harder to do than it was when I had my hands near the center of mass. Why is that? Well, I still need to provide a total force that is enough to balance out the force of gravity, but my left hand now has to push down, right, to try and equal out the torque. So because my left hand is pushing down, my right hand has to have an upward force that balances out the weight of the rod, plus it also has to compensate for the downward force of my left hand. So this really, I can't do it for very long because of that extra force that's needed. So, if you want to carry something efficiently, you'd want to carry it near the center of mass, but if you're like a pole vaulter who really needs to use that whole length, well, then you got to put your hands like this, and it's just going to feel a lot heavier because you have to compensate for that torque. It's a lot heavier than the one that I used. So here's an extended free body diagram for that example video that I just showed, and this guy here is supposed to be a kind of sad-looking pole vaulter, as I mentioned in the video. So if he's holding the pole with his hands equidistant from the center of mass, then his right hand and his left hand can apply equal forces and therefore equal torques that are going to, equal in magnitude but opposite in sign, so the pole won't rotate. So they just need to add up together to balance out the force of gravity. Now if he shifts a little bit, the free body diagram still looks the same. We can see that the force from the right hand needs to be bigger because it's got a smaller moment arm. It's closer to the center of gravity. And the left hand force isn't as big, right? So this is like if you're trying to move a couch and you're lifting it near the center of mass, but your friend's on the end, you're going to have to supply a much bigger force than they are. And then finally, if you're far out from the center of gravity, now in this case, if you let go with the right hand, you'd actually probably see the pole rotate around rather than rotating around the center of mass. It's going to rotate around where the left hand is. Um, so now the force of gravity is causing a torque, right? So the right hand needs to push down with a force that's even bigger than the force of gravity, right? Because it's closer to the pivot point, which is now the point where the left hand is. So the right hand has to push down with a weight, or sorry, with a force that's bigger than the force of gravity on the pole to balance out the torque. But then the left hand needs to supply an upward force that's more than twice the weight of the pole, right? Because it needs to not only balance out the force of gravity, but it needs to balance out the force from the right hand, right? So that's why you always want to try and lift something heavy near the center of gravity, so that you don't have to um, you don't have to compensate for these torques and end up exerting a much bigger force than you otherwise would.